Hey students, let me make a video solution for you for exam number 3 here, and then you hopefully can use this to kind of self-grade, partly to give you an idea of what you did right and wrong, and then partly to know your score, and so you'll kind of have a rough idea of your score before I get a chance to grade all these this weekend. Let's start with this first one. I think you'll recognize it as Ampere's Law right away. This is the second half of Chapter 30, the part that we didn't quite get to in test number 2. If you remember, we did the first half of Chapter 30. So this is the second half of Chapter 30, and it's Ampere's Law here. And it says here that we have a current density. Maybe you'll recognize this figure, and in fact, maybe a good place to get started is kind of grabbing the book here and jumping over here to chapter 30. And here in chapter 30, let's see, I guess that's section 2. Aha, here it is, section 3, Ampere's Law. And Ampere's Law then is listed right here where it says the integral around a closed loop of the magnetic field equals to the permeability of free space times the current that is enclosed by that path. And they actually do a really good one here, exactly what we're going to do, right? Yeah, it's right here, I guess. It's what happens if you have a uniform charge distribution. In fact, maybe you'll even recognize the figure and the image right here from the book, because that's what I just kind of copied and put here on the exam here. So the first part about this says that we have a current, okay? It's flowing along a very long wire. We'll need that for our symmetry argument. It has a radius of 1 centimeter. Its total current is 10 amps. And what is the value of the magnetic field? 3/4 of a centimeter from the center. So this would still be inside the wire. So this would be represented as Ampere's loop number 2 in this picture. Then we got two options. In A, the current is uniformly distributed. And so that means the integral of B dot ds around the loop is mu naught times the current that is then enclosed within that Ampere's loop. And this is probably the easier part. From symmetry, we could say B is a constant, so we pull it out. Also from symmetry, we would argue that this is cosine of 0 degrees. Then we just have then an integral of ds, which is the 2 pi r, and then that just equals 2I times the current enclosed. And we can use that for both part A and part B. So we'll jump back to that for part B. But in part A, then, we just have to think about, okay, how much current is enclosed? And this would just be the summation of di, remembering that the current density is di over dA. So moving the dA to the other side, we've got the current density times the area. And the easiest one to do is the one that you just have a uniform charge distribution, a current distribution, because once J is a constant, you can pull it in front of the integral, and then you just have the area. And then the area enclosed then would just be the area within inside of this Ampere's loop. And so calling the radius of the amp loop little r, and of course in the picture they show the little r for Ampere's loop number 1, but doing the same logic, little r for Ampere's loop number 2, this would be J times pi little r squared. And so we can put that into here. And so B times 2 pi r then equals mu naught. And the current inside then is this J, current density, times pi r squared. And by the way, notice that only worked for a uniform charge density. That's how I pulled it out. So this step here won't work in part B. And then, of course, to talk about the current density, if it's uniform, we can just take the whole current, so I'll call that I, 10 amps, over the whole area. And then using capital R as the whole area, we get something that looks like this. Which then you can see that we could cross out an R on each side, a pi on each side, and move the 2 to the other side. And so you get mu naught I times little r over 2 pi capital R squared. And to be quite honest, you don't have to do really all that much work for this first one, because that is exactly this equation right here, this 30.15 that's already been worked out for you. And so now it's just a matter of putting our numbers in, and if you'll kind of let me put those together, because mu naught is 4 pi when you times 10 to the minus 7, so when you divide by 2 pi, you just get 2 times 10 to the minus 7 for that group. We'll take the total current of 10 amps. We'll take the little r as 0.0075 and the radius as 0.01 r squared. And putting all that into our calculator, 2 times 10 to the negative 7 times 10 times 0.0075 divided by 0.01 squared is 1.5 times 10 to the minus 4 Tesla. Yay! And like I said, hopefully that went really well for you, since it was really already done. All you would need to do is kind of just plug and chug into that one. Now, the harder one is where the current density is non-uniform, and so we're going to have to actually perform this integration here. But we couldn't go back to this setup, and so maybe I'll start there. B equals, and I'll go mu naught times current enclosed, and then divide that by 2 pi r. And then over here, I will do, okay, the enclosed current is this integral of j dA. And so I'm kind of imagining then, here is the cross-section of the wire, and I'm just going to do kind of a shell method where to get this area, I'm just going to add up a ring and a ring and a ring. And of course, if you wanted to know a ring, you could kind of stretch it out. And the area, so that little area of each ring, would be the length of it. So this would be its circumference, 2 pi r. And then its thickness would be dr. And then, of course, each little ring would have slightly less of a current density, because a Gaussian distribution looks like this. You know, e to the minus x squared is a bell-shaped curve. And so the current is really concentrated in the center and then tapers off. And so we just have to do this integral. And fortunately, it's not a real hard one. It can be done by U sub. It might look a little hard at first. But let's go ahead and give it a shot here. Equals. And so let's take the equation for this field, the current distribution, this 31,800 e to the minus r squared. And then we have the 2 pi r dr. And we are going to add it up, going from 0 to 0.0075, because we're going to just, like we did in the first one, just add up the current within this part of it. Okay, well, like any integral, first thing you want to do is simplify it by bringing constants out in front. And so then we get e to the minus r squared r dr. And fortunately, that is the derivative of that. So this is sitting pretty for a u sub. So if we call u r squared, that means du is 2r dr. Or moving the 2 to the other side, I then have an integral, and this becomes e to the minus u here, and this r dr is 1/2 du. And our limits for r were from 0, and so putting in 0 makes u a 0, okay. And then it's 0.0075. For u, that would be 0.0075 squared. Now, this 1/2, we can bring it out in front and then even cancel it. So get rid of that. And then, of course, now you can see why the u sub works here. Because the integral of e to the minus u is just a negative e to the negative u. We can check that by taking its derivative, but if you take the derivative of that, you get the same thing, and chain rule puts down another negative, which brings you back to there. And of course, evaluated from 0 to 0.0075 squared. So this would be these constant terms, and then we can put in then our negative e to the negative 0.0075 squared minus a negative e to the 0, which of course is just a 1. So let's see how much current there is. According to the problem, the total current is 10 amps. So since we're only going out part way, we expect to be something under 10 amps. So maybe I'll do this one first and go 1 minus, so 1 and minus right there, that number, which would be e, where's e, to the negative 0.0075 squared. And so that's this quantity. Then I can multiply it by the 31,800 and also by a pi, and I get 5.6, let me do another decimal, 5.62 amps for the total enclosed current. All right, so now I can put that over here. So this is 4 pi times 10 to the negative 7. Total current is 5.62 amps divided by 2 pi and then 0.0075 since we are on the inside. And then again, like before, we can save a few buttons on our calculator by canceling that and writing it as 2 times 10 to the negative 7. Then times the 5.26. Then divided by 0.0075. Now, before I hit enter, I will point out, and probably not the best choice on my part, but this current distribution has this Gaussian e to the minus r squared, which, as you are probably noticing, our radius is not very big. I mean, even if you went to the full radius, you would have e to the minus 0.01 squared. That's e to the minus 0.0001. That's not quite 0, but it's pretty small. And we know that e to the 0 is equal to 1. And so this factor really is not playing much of a role unless the wire was much thicker. So even though this has a non-uniform distribution, the reality is it's not going to taper off. Or put another way, if the graph would probably look, instead of like I showed before, more like this. And maybe the 1 centimeter is right here. So the current is officially non-uniform, but in our small little piece that we're dealing with, it's pretty uniform. So because of that, I wouldn't be surprised if my answer for B isn't the same as what I got in A. And so I probably should have made it taper a little more, like maybe having e to the minus, how about 10,000 r squared, something like that, so it tapers. But watch what happens when I hit this. Yeah, it's still round. It's not exactly. It does taper off. Last time, you remember, we got exactly that number. But it has barely tapered off and rounds to the same number. And not a surprise. So I noticed that too late after I made the exam and go, that's not going to taper by much. But on the other hand, it made me feel good. I said, okay, well, when I make out the solutions, if I don't get a number that's the same as A, I should double check. Because this is definitely the harder problem. And maybe the hardest on the test. No, maybe not. Maybe part B. Yeah, part B of this one might be hard. I don't know. All this stuff is pretty hard. All right, well, like I said, I hope that went well for you. And by the way, I hope that you did well on it and that you did the homework problem. I was just thinking about number 30 or chapter 30, problem number 31 was part of the homework and was very much like this. Here it is. And so here we had this cylinder, we had a non-uniform current. Now, in this one, it was a proportional function instead of a Gaussian function. But other than that, the logic is exactly the same. So hopefully you did that. Actually, no, I said that homework problem. You know what I think that was? I think that was in one of my example videos. So if you go to the Canvas announcements and you look at extra examples done for chapter 30. Oh, I should have it up here. Oh, yeah, it's posted right here, November 13th. Yeah, you'll see that I did this one, yeah. And so hopefully you saw that, you studied it, you're ready for it, and you aced that one. All right, so because of that one, I'm going to change what I said. This problem was probably not as hard as it might have first looked if you had done that studying real well there. All right, we'll go on to the next one here. And so the next one is right from chapter 31. It's Faraday's law. We learned that there was an EMF produced, and it was proportional to the rate of change of magnetic flux. And magnetic flux is this integral of B dot dA. So here we have over here a rectangle that measures to be 3 centimeters long this way. Maybe I'll call this A. And 1 centimeter wide, so let me call that B. The near edge of the rectangle, let me call it C, is 2 centimeters from the very long wire. The very long wire carries a current, and there it is, a current that changes with time and is measured in amps. So we learned the right-hand rule that if you were to grab this wire with your right hand, with your thumb going in the direction of the current, you would get magnetic flux, with my green here, and the flux would, come out of the paper on this side and go in on this side. So we're definitely going to have some flux based on the current. And since the current is changing, the flux is changing. And since the flux is changing, there's going to be an EMF. And so our goal here is to calculate how much flux first and then the derivative. So I'll leave the derivative alone and just look at a flux calculation. And the first part of this is to recognize the direction of the magnetic field is going into the paper, and the area vector is also into the paper. So there we have an angle of 0. Actually, you could argue 0 or 180 degrees. And so within a plus or minus, which we take the derivative, we're going to get either a cosine or a negative cosine. And in fact, this exact calculation is done. Where did your author do this flux calculation? And I know I did it in the video lecture. I think it's... No, must be... I was thinking it was at the end of chapter 30. Yeah, right here. Here we go. And so the author does do this calculation and comes up with this equation here. Now his A and C might be a little bit different. Yeah, my A and B are a little different than his backwards, but his C is the same. But that aside, let's see what we get, and hopefully we get the same thing. And so I'm going to put a negative of the derivative and leave the derivative alone here for just a second. And here's where we're going to have to kind of go back to some previous chapters to remember that the magnetic field from a long wire on the outside looks like this. We just did a problem for the long wire inside. This is on the outside. So there's the strength of the magnetic field. And then dA, I'm going to imagine adding it up in this rectangle, but I'm going to be adding strips, because this little formula here says that the magnetic field changes as you go further out. So I need to take the amount of flux from each little strip, which would be the field times the area, calling the area its length A and its thickness dr. Then I would add them up, starting at R equaling C and going out to C plus B. And then again, like all of these, take a look at your calculus, and you'll have to kind of start asking yourself what things in here either don't change, or change only because of time, or change only because of space, or both. And so as I look at this, the mu naught and the 2 pi are constants that don't change with space or with time. So So I will move them in front of the integration of space and the derivative of time. Now the current here is the same at a given moment in time, the same everywhere in space. So I'll move the current in front of the integral of space, but I need to be able to take its derivative because it changes with respect to time. Now the A, I guess, could also come all the way out to the front because it does not change with space, and the size of this rectangle is the same no matter what goes on, and also with time. So I'll move that out to here. And then over here, I just get the dr over r, which is from C to C plus A. And so this right here is a natural log integral. So this would be the natural log of C plus A over C. And at least in part A, where it says here, what is the EMM induced in the rectangle if the loop is stationary? That means the distance away, C, doesn't change, and also the dimensions of the rectangle, A and B, don't change. So this right here, once I do the integral, does not change with time. So that actually, too, could be brought now in front of this time derivative. So this would be minus mu naught A over 2 pi. And then I would have this ln of C plus A over C. Oh, wait a minute. I think I dropped it. This should be C plus B. Yeah, C plus B, because I'm going from C out to the end. C plus B, C plus B. Okay. Yeah, I like the looks of that better. Okay. But then, right here is the derivative of the current. So the derivative of the current would be this 5.25. And the derivative of the sine function would be cosine function. And then the chain rule would give me a 6,283, the angular frequency, out in front. So the EMF will be some value here, which we'll calculate, times cosine of 6,283 t. So this probably would read better when it says, what's the EMF? It should, say EMF is a function of time. Obviously, it's got to change with time since the current is changing with time. It's not just like one value of the EMF. Something has to be changing. And then grabbing the calculator here, maybe I'll just leave the negative alone. But taking advantage of that same thing we've been talking about, mu naught divided by 2 pi is just 2 times 10 to the negative 7. Times the A, that's the 0.03, times the natural log. And C plus B would be 3 centimeters divided by 2 centimeters. And there's no need to convert those to meters since they're the same units. They're going to cancel out. So if we convert it to meters, they cancel the same way. It's still 3 over 2 of meters, inches, whatever. So I'm just going to go and leave it in centimeters and just call it 3 over 2. Okay, and so this is the 6283. And then this is the 5.25 and hit enter. And so we don't get much. Not too surprised. It's pretty small. Our current's not that strong. Our loop's not that close. And our rate of change of frequency is not that great. In fact, This must be 1,000, because if I take this and divide it by 2 pi to get the frequency, that, pi is 3.14, so you double it, you're at 628. So this must be 1,000 hertz. So it's just not that high of frequency. Anyways, all of that just leads to a number it's not a big number, but it is measured in volts. So I guess I should put my units there, volts, and say, all right, so here is the EMF for part A, and ones that we did problems like in class. And so that one's not a surprise. But here's a more challenging one. In fact, let me grab the book here. If I go over here to 31, go to the problems that you did. One of the ones you should be doing is this one, a long straight wire carrying a current I, there it is, in a plane, rectangle. And so this was one of the homework problems, and other than things are a little different, this is the one that we basically just did. I think they give a picture of it, but they gave a picture a little earlier. If I remember right, they did. Yeah, right here on number 8. They have a current, and then they have the rectangle, and they said use this for problem number 8 as well as number 67. So again, hopefully on the homework you did this one, and so that one you just kind of aced. I will point out you also did 66 on the homework, because 66 and 67 were part of the homework, and this is derive an expression when something is then moving near the wire. And the part B is sort of like this one, because we have it moving, but it also still keeps the current varying. And so we've got two things changing at the same time. And that's what's going to make it a harder problem. See, because it says, what is the EMF induced in the rectangle if the loop is now moving to the right at this speed? And so going through the same logic, we would say my EMF is minus the derivative. And everything in part B is just like we did in part A. Here is the flux calculation. Here's the strength of the field, the area, the angle. And so let me pick up right here. And so this would be this integral from C to C plus B of mu naught I over 2 pi r A dr. And then when we do this little step where we have a derivative of time and an integral of space, we can study all this again, and we still get the negative, we still get the mu naught, we still get the A, we still get the 2 pi. So all of these come out. The current changes only with time, so I can bring it right here. But here's the interesting one, is that when I do this integral, which goes from C to C plus B, which is, again, still going to be this natural log. But that natural log is going to have a C in it, and C changes with time, so we have to take its derivative as well. In other words, we can't just do this step. This step right here is going to be a little different, because we can't just take this and move it in front of the time derivative. Back here when it was stationary, the values of C and B, which were part of this answer, didn't change with time, but now they are. And so we're going to end up having two things that change with time. And so that means we have to take a derivative of product. So we've got the product rule that we're going to have to to mess with. All right, so let's see. Why don't I just write this as ln of c plus b over c? Because then I can write this as minus mu naught a over 2 pi. And now I will take the derivative of the product. And the product rule is you take the value of the second multiplied by the derivative of the first. So here's the second and derivative of the first, plus the first times the derivative of the second. And of course, you can now see that this first term, when you do a distributed here, this first term is that one right there. And this term we didn't have back in A. It's basically saying the derivative of this, if it doesn't change with time, is 0. And so that's why that one went away. And so really we just have this added piece. So with that in mind, why don't I just make it a little easier on myself and saying this, this, and this is all of these, which I already know that answer. So this is minus 8.02 times 10 to the minus 5 cosine 6283t. And then this second term would be the minus mu naught a over 2 pi from the distributive. Then it would be the current, which is 5.25 sine of the, why don't I just call it omega t and save myself a little bit of work, 6283. But then I have this derivative of a natural log. And at first it looks kind of scary because it's a derivative of a quotient. So not only do I have a derivative of a natural log, but then we got the chain rule, which is going to have a quotient in it because the c changes both in the top and the bottom. And that's kind of messy. And so I'm going to recommend anytime taking the derivative of a log, avoid the quotient rule and even the product rule by taking advantage of the property of logarithms. And in this case, when two things are divided, you can go ahead and subtract the natural logs of them. And that way, I don't have to do something more complicated. All right, so this first one, minus 8.02 times 10 to the minus 5 cosine, and let me just write that as omega t also. And then right here, here's my minus mu naught a over 2 pi. Here's my 5.25. Here's my sine omega t. And fortunately, this isn't too bad because when you take a derivative of a natural log, you get 1 over that quantity. And then the chain rule is the derivative of the argument. And the derivative of c is the chain rule. B doesn't change. So back here, this is moving to the right. C changes with time, but not B. And in fact, this C changing with time is the rate at which it's moving. That is the velocity. So that's where the velocity is going to come into play here. Likewise, derivative of this natural log c would be 1 over c times dc dt. So both of these have this velocity term. In fact, why don't I just put velocity on the outside and cross those off? So that this is minus 8.02 times 10 to the minus 5 cosine omega t. And now, let's just put in our numbers. You can see we're going to get a, well, maybe it's not so obvious, but this c is smaller than c plus b. So that's going to be a negative number. Together with that negative is going to ultimately make a positive here. And then we're going to have a sine omega t. And then there'll be some number here. So let's grab the calculator here and put this in here. And I'll include the negative to show you that this will change to a positive. And let me take advantage of that same thing, 2 times 10 to the negative 7 here, times 0.03 for A, times 5.25 here. Let me put in parentheses. This would be C plus B. So that is 1 divided by 0.03. I'm going to be careful with my units here. Put that in meters, because remember the C is 2 centimeters and the B is 1. Minus 1 divided by, and then the C is 0.02. And then the last one is times this velocity, which writing it in meters is 0.025. And if I hit enter, I get 1.31 times 10 to the minus 8. And I'm just checking here. I think that's right. Kind of looks right. Wish I would have given it a stronger number here, because this term's so much smaller. You really could ignore that. So the current's changing so quickly that the induced EMF is 1,000 times greater from the change of current than the motion. And so from a practical point of view, you could just say, well, don't even worry about this one. That's not playing into role. But if it would be about the same level if I had this like moving 25 meters to the right, 1,000 times more. So probably should have done that. Okay, anyways, but I'll put a box around it because there's the answer. And of course that omega is that 6283. That would go in there and in there. And so 2 pieces. And that's, like I said, probably the hardest part. Although, if you just kind of blindly follow the math, you can just see you're taking a derivative of a product. It's no different than A, just harder math because we got 2 things changing at the same time. But we know how to deal with the derivative of 2 functions. It's why we call it the product rule. All right, well, let's move on then to number 3. Number 3 is our little discussion here on DC circuits with inductors. And maybe the first thing to do is, study the circuit here. Notice that it can be simplified because these 2 inductors are in parallel, and you can combine that and get its equivalent. So the equivalent, and since they're in parallel, is 1 over L equivalent is 1 over L1 plus 1 over L2. And so taking them to be the same value, you get 2 over 35 microhenries. So when you take the reciprocal, you get 35 divided by 2, which must be 17.5 microhenries. So I'll put that right here. 17.5 microhenries is the equivalent inductance here. And then a little harder to see, but we did talk about this in chapter, 28, when we're dealing with resistors, that even though there's something in between them, once you look at this as being one equivalent, you can see that that resistor is in series with the equivalent of these two inductors, which is in series with this one. So basically, these two are in series, and so we can put our resistors together as if they're in a series. And in that case, we just add them. Let me put a switch somewhere. So this is our equivalent circuit. And hopefully that's what you get out of this little first comment here. Study the circuit at the right and given these values. All right. So this means we can think of this more complicated circuit as just a simple single inductor and single resistor. And I say that, and I'll grab the book again, maybe to jog your memory here. But as we got started in chapter 32, we did solve, here it is, I guess it's over here, starting here on section 2, the resistor and the inductor DC circuit when you are closing or opening the switch. And this would be the current. And in fact, this right here is the graph of that equation where the current's building up, sort of like the charge built up in the capacitor. We even have a time constant here, which is the L over the R. So I'm going to take advantage of that. Okay. Although we really won't need that till part C, because I'm hoping what you remember is this discussion. It says, what is the current through the switch S? And so looking at this equivalent one, once at the moment the switch is closed. And what we said is that when you did this, the inductor, right as the switch is closed, acts like an open circuit. In other words, it actually produces as much back EMF as the power supply. So in this case, 20 volts. And so there is no current. And so that's what you get with an open circuit. So this one should have been maybe the easiest one on the exam. Just, hey, what is the current right when you close that switch? Well, zero. That was the whole argument of the inductor and Faraday's law. Now B here is where, after a long period of time, we'll see for a DC circuit, not for the AC circuits, because the current and the voltage keeps changing. But for a DC, after a long period of time, everything settles down. And you only get a voltage. Remember, the voltage of an inductor is minus L di dt. So things have to be changing for there to be any back EMF. And so that's why we say after a long period of time, you can think of the inductors as just being a short circuit, a wire. They have no voltage in them. And so if you think about this equivalent circuit with no inductor, just a wire here, then the current would just be Ohm's law, V over R. And so we've got the 20 volts, and divided by 100 ohms gives you 0.2 amps. And so that one's not much harder than this first one, but definitely easiest one, and then this is the second easiest one. Now, the one that's going to involve a little bit of calculator work here is the current in this switch, 100 microseconds. So using that little formula here of 1 minus e to the minus t tau, we can then figure out what the current builds up to. So this V over R is the 0.2, and I get 1 minus, and the time is 100 microseconds. The time constant, the L over the R, would be the 17 micro. Let me change the micro to 0.0175 divided by 100, which would be 0.2 zeros, then a third 0, 175, 1, 2, 3, 4, 5, 6. So that would be 175 microseconds. So down here, I can put 175 in the same units. So I've got top and bottom of the same units, which is good. They want to cancel off. And so we'll need that because we're taking e to something with no units. We should be. And so you got 1 minus, no units with no units. And this is the 0.2 amps. And so the answer will be in amps. All right, so putting this in here, I'll maybe go 1 minus and just go E. I guess I have a negative 100 divided by 175. And maybe I'll just hit enter. So this comes out to be about 44% it has built up. So we'll take that 44% and multiply by what its max is going to become. And saying at this point, we are at 0.087 amps. I suppose if you want to call that 87 microamps, great. And if you wanted to call this 200 microamps, that's great too. But either way, we're saying the same thing here. So there's our 3 in our chapter 32. Now, this is an interesting one, and maybe this is a pretty challenging one too. I'm glad number 3 wasn't too challenging, because this one is. And then I think number 5 is pretty straightforward too. So 3 and 5 are pretty straightforward, but this one in particular has got a lot going on here. It kind of helps you though, and here's actually one of the challenge of an electrical engineer has with working with electric motors is they're an AC electric motor. You have an AC source, you're running it through your wires, but you've taken your wires and you've made them into little coils to make the magnetic field to run the motor. And that acts like a little inductor. And of course, then the wires act like they're resistors because you have a length to them. And so you essentially have this AC, and I'll call it an R, but no CL circuit. But as you'll see here and study this, it actually makes a lot of sense then to add a capacitor in series with this motor. Now, this is right here being the motor. The motor has got the resistance and the inductance. And so let's read it, and hopefully this all makes sense. But I was hoping the pictures I gave you would help if the words didn't make sense, because it says an electrical engineer builds an electric motor using, and so here's a long wire, 100 meters, and it's pretty thin. It's 22 gauge, which they give you the diameter. To make the motor, the engineer then twists this wire into a solenoid. So it kind of looks like this. And you have 114 loops. And then the diameter of this, pretty good sized diameter. So we're talking, here almost, well, it wouldn't fit on the screen here, but, almost 30 centimeters here. Where's this one here? This is a little ruler here across the page here. But this goes to about 17. So if you double this, you're at 34. So it's not quite double this, but it's good size windings here. Not too much different than, a little bit bigger than the one we did or will do in lab this week. For those of you who already did this lab Thursday afternoon, know what I'm talking about. And the rest of you will, at least in person, we'll do it on Friday morning, tomorrow morning. Okay, but this tells us a lot here. They tell us the length of the solenoid. And then the nice little hint. This information tells you what the resistance and the inductance is. So we'll have to go back a couple of chapters to chapter 27 to remember that here's how you get your resistance. And for the length, we'll go 100 meters. And for the area, we'll go pi times its radius. So I'm going to take the diameter. Cut it in half for radius. Then convert it to meters. Okay, so there's the length, and there's the cross-sectional area. The resistivity is where we're going to have to jump back to chapter 27. I believe it's table 2. There it is. And we'll take the copper, 1.7 times 10 to the minus 8. Okay. So 1.7 times 10 to the minus 8. So by the time you take all these wirings and hook it up, trying to get a lot of current to go through our wires, because we're trying to make a strong magnetic field so we can make a strong motor here, we get what? So 1.7 times 10 to the negative 8 times 100. Divide by pi. Also divide by 0.322 times 10 to the negative 3 squared. Hit enter. And we're looking at about 5.22 ohms of resistance. Yay! If you remember the lab we did on this resistivity, that was about the resistance of that 20-meter wire, so 5 times shorter. But it wasn't copper. It was a nickel-silver alloy. All right, now, where we start getting into the stuff related for this chapter is all that wire then makes this act like a little inductor. And there's a lot to this problem. So I hope you don't go back and try to derive the inductance here. But when we were first introduced to inductors in chapter 32, the author in the first example right here said, hey, let's just take a solenoid. And it says, okay, how many turns? What's the cross-sectional area of the solenoid? The length of the solenoid? And so it's equation 32.4. And says, okay, mu naught times n squared. Now, I'll put area and length, although I want to be a little careful. This is not the same area as what we just did for resistance. It's not the same length. And so when you coil it up, I don't have anything that I can use to kind of show coiling it up. Yeah, maybe this will work. But, if this is the long wire in my first calculation, this was its length, and then how the current flowing through that little end point is the area. But now, as I wrap it into a solenoid, okay, and we're talking about the magnetic flux through this area. So we're talking about an area that has to do with the diameter or the radius of our solenoid. And when I got up to get that, I lost my pen. Oh, here it is. Okay. So this would be 4 pi times 10 to the minus 7. And the number of turns is 114. And then this area would be pi r squared. So let me take this 0.279 and cut it in half and square it. So that is the diameter of the solenoid here. And then, of course, once you start wrapping it like this, you can see that it's not going to be nearly as long as when it's like this. And so if you wrap it up, in fact, you can kind of see if you wrap it real tight, the whole length would be the diameter of the wire times how many loops you have. In fact, let's just see that. The diameter is 0.644 times 10 to the negative 3. And we do 114 loops. Yeah, that's going to make 7.34 centimeters if we made our solenoid, real tight, one wire right next to another one. So, this picture doesn't show them real tight to each other, but what you'd really want them is nice and tight. Of course, you also want a little insulation on them so that the current goes around the loops too. So you don't want just bare copper touching each other. But in either case, there's our length. So our length is 0.0734. And that's going to tell us our inductance. So grabbing my calculator, 4 pi 10 to the negative 7 times 114 squared times pi times 0.279 divided by 2 closed quantity squared divided by 0.0734. I get an inductance of 0.0136 Henries. I suppose you could say 13.6 millihenries just as well. Now, I did all this because it then says this motor is then plugged into the wall socket and a diagram of the equivalent electrical circuit is shown on the right. So this resistance is in series with our inductor. And so we really have an AC circuit where we have an inductor and a resistor, no capacitor as of yet. But we did learn that the current in it has to do with the impedance. And the impedance is the square root of R squared. And then the reactance of each of the inductors, or inductors, plural, capacitor. In this case, then, we need this reactance, let me call it X sub L, because that's omega C. And this is the one that I said, I hope you commit this to memory. But if you plug it into the wall, at least in North America, the frequency is 60. And so remember that. And then also it's worth memorizing that if you multiply that by 2 pi, you get the famous 377. So this is 377 times the 0.0136 to figure out what the reactance is. So if I multiply those two together, I get a reactance that's in the same ballpark as the resistance. So the resistance was 5 and change. The reactance is 5 and change. Okay. So if I put this into here I get 5.22 squared added to 5.13 squared, and we'll just say no capacitor. And so my impedance, the part that's stopping the current from flowing, is coming from both the resistor and the inductor. And so 5.22 squared plus 5.13 squared inner, and taking the square root of all of that means that we have an overall impedance of 7.32 ohms. And so if we wanted to know the RMS current, and I'll pick on that because it says what is the electrical power. And so going to our chapter 33, we had a section after talking about all this about the power in our AC circuit. And so they took the current times the voltage and ran through some mathematics here. But what I'm going to do then is use this equation right here. I guess it's 33.31, where I can get my average power by looking at my RMS current, my RMS voltage, and then this power factor. This cosine phi is called the power factor. And phi is the discussion a little earlier back here, where you can get your current from the impedance and you can get your phase angle from the reactance and the resistance. So let me do that. So my RMS current would be my RMS voltage divided by my impedance. And so the other nice thing to keep in memory here is that when you plug something in North America, not only do you have 60 hertz for your frequency, your voltage, RMS, is 120. Your peak is about 170. So using the RMS of 120 and divided by 732, this should give me my RMS current. So 120 divided by my last answer. And so we're looking at a significant amount of current. Not an overwhelming amount of current, but overwhelming for such small wiring, definitely. Which I guess is, it's like, okay, there's some other issues too, but ignoring all these other issues, this is not a fully designed motor. But we're going to be operating at 16.4 amps. So it'll be a little bit more than kind of a, many of your plugs, depending on the age of your house, can be 15 amps, but a lot of them can be the higher 20. And so this could be in your garage, this could be in your bathroom, your kitchen. They usually have a 20 amp one there. Outside, it probably depends on the age of your home. My home, sadly, has a 15 on the outside. And my compressor needs about 16. It's really obnoxious. But I plug it in the garage. That's cool. But that being said here, calculating the power then, it looks like I'm going to one out of room here. Maybe I'll flip it over here. It's okay. So my power, my average power, is this RMS voltage. Now, maybe I'll write it VRMS, current RMS. But here's the big thing, the phase between those two. And let's talk about this, and this will be the strategy of the electrical engineer. But let me put 120 here for the voltage. The current, what did we say, 16.74? So 16.4 amps here. And then we're going to need cosine of this phase angle. And that phase angle is the inverse tangent of the reactance between the inductor and the capacitor and R. Which at this point, we don't have a capacitor. And maybe now you're beginning to see the advantages of adding a capacitor to this. But your reactance was our 5.13, and the resistance was 5.22. So they're almost the same. So this is going to give me an angle very close to 45 degrees, since we know the inverse tangent of 1 is 45 degrees. So inverse tangent of 5.13 divided by 5.22, and I'll get 44.5. And so putting that into here, you'll see, and of course, cosine of 45 is the root 2 over 2. Yeah, 0.707. So this should be very close to 0.707. Yeah, 713. And then times the 16.4, and then the 120. And so we are looking at 1,404 watts. Yay! And so there is our answer to part A. You know, what is the power of this motor? I don't know. Did I do that right? 120, 7.32, 16. Okay. Nice. All right. It just didn't quite seem like the right number there. All right. Now, I suppose if I wanted to, I could take this wattage and divide it by, and it's probably been a while since you did this. We did it mechanically back in Physics 121, but 746 watts is 1 horsepower. And at least here in the United States, we often list motors in horsepower. And so this is a just shy of a 2 horsepower motor. And so pretty good size motor. One, like I said, wouldn't, little too big to be like a garbage disposal, but could be one on a good size table saw or an air compressor, maybe a good size air compressor. Like I said, yeah, just above 15 amps and there. But we're also not utilizing the full capacity of this motor, which is where B comes into play. Because for B, we can start off and maybe do a little bit of thinking here. How can we get more power out of this? And you can see that increasing any of these 3 factors, and maybe better all of them, we would get more power. Now, so we're plugging it into the wall, so this number right here doesn't change. That's going to be 120. However, this current is the RMS voltage divided by the impedance. And so the smaller you make the impedance, and now you can begin to see, if we can't really change what we already have, the wiring and the loops to make the magnetic field, we could add a capacitor here, balancing off the reactance of the inductor. And if we make them exactly equal, this is as small as this could ever become. So the best we would ever expect to do would be the voltage of the RMS divided by just the resistance, because we exactly matched the reactance of the inductor with the reactance of the capacitor. And so this is the one of two reasons why we would want to maybe add a capacitor in here to try to get a lower reactance. And so the capacitor kind of undoes the electromagnetic effect of the inductor. Now, the other thing, though, is this gets greater the closer you can get it to 0, because cosine of 0 is 1. And if you look at the phase factor, that occurs when the reactance of the inductor and the capacitor match also. So fortunately, these aren't competing with each other. These each max out when the reactants match. And really, we don't even have to calculate the power. It just says what size of capacitor should be added in series with the motor to maximize the power delivered to this circuit. And then here we have the diagram of the equivalent is over here. So what we really need to get is our XL matching our XC. Now our XL was already determined at 5.13. So this is 5.13. And our reactance of our capacitor is 1 over omega C. And remember, omega for the wall plug in North America is 377. So if I grab my calculator and go 377 times 5.13, that's what I get when I multiply those together. And bring the C to the other side, so I want the reciprocal of that. And we're looking at 5.17 times 10 to the minus 4 farad. About 517 microfarad capacitor would do it. And that would bring the current in alignment. And just as an added piece, although this video is getting kind of long, we could then get this motor operating much higher. So this would be 120 divided by the resistance, 5.22, because now it would be operating at 23.0 amps and cosine of 0 degrees. So that would be 120 times the last answer, and we are now looking at 2,700, I'll just call it 60 watts. Almost double. 746. And so we're looking at a 3.7 horsepower motor. Really a good size motor, which you can imagine with this much current and that much voltage plugged into the wall. This is how we would maximize that. So without that capacitor, we got just a poor design. We've spent a lot of money on something that does not delivering what it could and should in order to get it. Anyways, hope that one makes sense. That was a little bit of a tough one here. It's on AC circuits. They too are always a tough one alone, let alone all this other stuff. We're trying to mix something in that was practical. Oh, that's the wrong one. Here it is. And so here, then, let's go ahead and wrap this up in the one I said that chapter 34 would be pretty straight. The first thing is to recognize in the description, regardless of what the description, if this is one of the electromagnetic waves. And so section 34.7 went into the spectrum that, there's all kinds of electromagnetic waves. There's ultraviolet, there's visible light, there's microwaves, there's radio waves, there's millimeter waves, there's gamma rays. The list goes on. And so hopefully right here, regardless of, what we're using them for, right here, where it says we have a high intensity ultraviolet laser right there. And this UV light then is given in a way that we have an electromagnetic wave. Now, in this case, we're going to make it a pretty small wavelength. That's why it's UV. We're going to, blast it onto a silicon wafer and dig little channels so we can make microscopic channels where we're going to then dope it and, fill it in. And so we can get something like 1 billion transistors for every square centimeter, some ridiculous amount. And that's, how we build all of our semiconductors. But without getting into the actual lithography of the whole process, we are supposed to know here that a right angle grid, where's the textbook here, is formed between our electric fields, our magnetic field, and the direction of travel. And so that was my hint and warning to you that something like that will be on here. And so this section here kind of is shown right here in section 3 that the electric field, the magnetic field, and the direction of travel form an XYZ grid, coordinate system. And so they're all mutually perpendicular to each other. So if we are calling the direction the laser travels the X, and the magnetic field is in Y, then the electric field must be along the Z-axis. And so there's the first answer. It's got to be along the Z-axis. The other thing here is the strength of the magnetic field is, and the ratio of the electric field and the magnetic field is the speed of them, which now that we've discovered they're the speed of light, which is the square root of mu naught epsilon naught, doesn't surprise us then, because this is both the electric permittivity and the magnetic permeability, and that is how the two interact with each other as they move through open space here. So to get the strength of the electric field, I would just go 3 times 10 to the 8 and multiply it by the strength of the magnetic field, which is a pretty strong field here. But this is a high intensity laser, very, very high intensity. And mostly, though, because it's focused to a small spot. And so intensity is energy per area. And so you don't have really that much. Well, I should be careful. It still is quite a bit of energy, but it's not an overwhelming amount of energy. I mean, if you put your hand in these beams, they, don't cut off your hand. It certainly blisters your hand right away. So they're pretty dangerous in that sense. But they, it's the energy itself is not overwhelming, but it's the energy per square area. They're focused so tightly. And so the field is really, 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 really strong here. So if I take 3 times 10 to the 8th and I multiply 1.26, I get 3.78 times 10, and I believe that's to the 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. And then this would be newtons per coulomb or volts per meter, whichever set of units, since we've been using both, would be useful. So there's the strength of the field. Now the C is about how much time does it take, and distance equals velocity times time. And as we already talked about the velocity, you could say time then is distance divided by velocity. This is not traveling far. I think on the practice test, I had the waves traveling more of a substantial distance. Maybe it was from here to the moon, and it was a radio communication, or maybe it was a satellite. Not sure, but some of these distances can be really big. But for distances that are on the Earth, these are really short amount of times. Could be because light travels really, really fast, at least on our scale. It's always interesting to ask somebody if, does light travel fast? And they're like, oh yeah, goes around the world 7.5 times a second. Wow. Yeah, but it takes 100,000 years to go across our galaxy. So really, is it that fast? So it really kind of depends on your perspective. And so when it comes to astronomy, I would have to say, no, light is pathetically slow. That's a little weird to hear. In either case, the time here, I'm sorry, I typed this in wrong. It's 2.25 divided by 3 times 10 to the 8th. Yeah, and about 7.5 nanoseconds. 7.5 nanoseconds. And then finally, to finish up the exam here, at what rate? And so wavelength times frequency is the velocity, was our third one. So the frequency would be c divided by wavelength. That's 3 times 10 to the 8th. The wavelength is 250 nano. Let me change nano to 10 to the minus 9. And this will be very, very high frequency, which, if you look back on that chart, that's where the ultraviolet light was. It was way up at the top. In fact, maybe we'll grab the chart here in a second as we wrap up. But this is 1.2 times 10 to the 15 hertz. Let's see, 10 to the 12 is tera. It's after tera. Peta. So peta hertz. This is crazily high frequency. And that's this section 7 in the book about the whole electromagnetic spectrum that we started this. And so we're looking way up here, not as high as X-rays, but ultraviolet, right in here. Yeah, 10 to the 15, just above visible light, right? Which is why we call it ultraviolet. It's just a little bit higher in frequency than the violet. Whereas the infrared, just a hair below the red, although actually it's a pretty broad area there. All right, well, hope you did well on the exam, and I hope this helps you learn the material as well as give you an idea of how well you did, because I know that you've got a tough decision to make about, do you keep your score or do you take the final exam and try to do better? All right, take care.